record. So we're looking at vectors
Will
and
you record going over the paper one?
I don't think I have recorded that.
Right,
It's
okay.
to do with the fact that paper one can be reused.
Oh, right, okay.
So you can't, yeah, if you put that public, yeah, if you put that publicly, but I'll send you the PDF as long
Yeah.
as you don't share it. Because if
No.
they reuse some of the questions, then that can void any of the, okay?
Yeah. Okay.
So we are looking at vectors and scalars today. And a vector, it says here, is a quantity which has both magnitude and direction. So usually the vector that I tend to use as an example, the best example is you've all watched the weather forecast.
Mhm.
Yeah, so you saw all those lines coming through showing us the wind directions. So there you go. So you've got a vector there, a direction, and sometimes you see some of the lines being bigger than other lines, and they would tell you that the magnitude of the wind is stronger. So that's one thing where you could see vectors in real life being used, and that's probably one of the one that you will see the most. But any 3D type games as well, people designing games, they use vectors to represent people walking and displacements, etc. So it's used quite a lot in terms of mathematic modeling. So that's why it's interesting to see what they mean by that. So gravity is a vector because gravity is like a force that pulls us towards, that keeps us on Earth basically. So it's a force. So depending on where you are on a different planet, the gravity force will be different. So if you're on, that's why they tell you your weight on Earth would be a certain mass. So the mass doesn't change, but your weight would change. So if someone tells you you weigh, I don't know, 11 stones on Earth, if you go to the moon, you'll see them bouncing about. That's because there's less gravity. It depends on the size of the planet they're on. Okay, so their mass stay the same, but the weight differ. So
Kids in my school that are on another planet, to be honest.
So if you want to lose weight, you
I'll-
just move to a different planet that is smaller than ours.
I'll see you there.
So velocity is another one. So we tend to talk about speed, but in physics term, they give you the magnitude of the speed plus the direction it's taken. And that's quite important when you work with particles, like in physics, they would use that quite a lot. So we mentioned force. So the difference between the vector and the scalar, what they call a scalar, is a quantity that has magnitude only. Okay, so if I was to say you, for example, just a time, you don't have the direction of the time. Okay, you could argue with that and say, oh, minus 2 hours was 2 hours before, so we can say that it's behind us. So when they talk about speed or average speed, so how fast I am going, for example, it's an average speed. And a mass. So the mass is just a scalar. Okay, doesn't change. It's the amount of body. So
Sorry, can you go back there for 2 seconds?
oops, sorry.
Time, speed.
So time, speed, and mass is what we call a scalar. So it's got a value, but it's not associated with a direction. It's only got a magnitude. Time,
Okay.
speed, and mass, for
Thanks.
example. So when we name a vector, we use letters, okay, which is algebra, something. So we use lowercase or underline letter, for example. So if I've got a point A and a point B, we can call that the vector is named AB with an arrow at the top of it. So that's how you would see it named. Or sometimes they can just put a small letter U. So this time you can see the U is bolded. So on some paper, you see them with a bold, or they just put an underline just under the U. So you've got 3 ways you see on papers: bold letter, underline, lowercase letter usually, or the 2 points that makes the vector with an arrow on top of it. So that's how you would define it, but sometimes you represent the vector with just numbers. So we call it representing the vector in component form. So for example, remember we said you've got a vector u, here they called it d, and it's with its component form, you'll have an x form and a y form. About the same as when you had your x and y coordinates, for example, on a point. This time they put them in a column to show you that they're mentioning vectors here. And again, you can have x and y. We'll see what they mean, okay? So column vector, sometimes they call it. So two cases here. We've got 2 points, C and D, the vector CD between those 2 points. So this time we've called it W with an underline for it. And FE, which is called Z in our case with an underline. So CD in a component form is going to be on the x-axis 4, which call it 4 units. So as you can see, to go from C to D, you need to go 4 along the line and 2 up. So that's why you've got 4 in X and 2 in Y. And that's how you could represent CD. Okay, so now for FE, this time we're going to go 2 along the right side, so that'd be positive 2. But this time we're going down the way. So when you go down, they usually put a negative value. Okay, so it's just to represent the vector FE. Instead of going up, it's going down. It's a bit like when we had different gradient. You know, when it was going down, it was going negative, the line, and then when it was going up, it was going positive. So they use a similar approach to that. Okay, so it's not difficult to represent or write it in component form or in different forms. Okay, so now they mention the fact that vectors, they are equal. So you can have 2 equal vectors only if they both have the same magnitude. So if the vector's got the same length, so if you were to represent a vector on during the weather, you would put a certain length, which means the magnitude of it, and they go in the same direction. So if you've got 2 parallel vector, for example, 2 parallel vectors, and they go into towards the same direction and they've got the same length, we say they're equal. They don't need to be one on top of the other, as long as they are parallel. We still say that they are equal vectors, okay? So if I give you these vectors here, so we've got A, B, C, D, E, F, G, and H, and I ask you which vectors are equal. So you can have a look and decide.
D and H.
So A, N.
I said D and H.
So D and H. So remember we said they need to have the same magnitude
Obviously magnitude in
and the
terms
same direction. So at the moment, D and H, they've got the same direction, but then you can see that H is slightly bigger. It goes 4. So 4, 0 for H, whereas it's going to be
G and A be one.
Is it
Sorry?
A and B?
G and A.
So G and A. Yeah, so G and A, they've got the same direction. Yeah, and you can see that it's 3 along, one above, 3 and 1. So G and A are equal, definitely, yeah. So I'm looking if there's anyone else. No, the 2 that are equal here are G and A.
Sorry.
Bless you.
Thanks.
So sketch the vectors 2a minus b and 2a minus b. So if you've got here, so here we decided what was 2, the only 2 here was a and g. So if you're asked to sketch 2a as a vector, it just means we're going to have to double. So 2a will go in the same direction as a, but it's going to be twice the magnitude of a. Okay, so how do I double this vector? I just put it twice, nose to tail, basically. Okay, so that would be doubling a. So I started with a vector a 3 along, 2 up. Now it's going to be 6 along and 4 up. So if you notice, each component in the x and the y direction, they've doubled. So that's how you sketch 2a. Now, to sketch negative b, at the moment, b is going down with that magnitude. So we're going to use the same magnitude, but instead of going down, we're going to go up the way. So we're going to flip the vector itself. So to sketch negative b, you just change the direction and you just use the same magnitude. So that's how you do minus b. Okay. So now how do we represent 2a minus b? So I've done 2a here, and I've changed the direction of b to make it minus b. So 2a minus b, you think about going from the tail of 2a, and we're going to bring now negative b on the nose of 2a to become a new tail. And this is how you represent 2a minus b, by linking the two new points that we have. Oops. So 2a minus b is this new vector here that will go from, so if I was to represent 2a minus b, I just need a pen color. So I would go red, for example. So 2a minus b would be represented by this new vector if I had a proper ruler. Okay, so that's 2a minus b, the new vector. And then you can write as 2a minus b and call it whatever name you want. Okay, so that's how you would represent it. So any two vectors can be added in this way. So if I say a plus b, you just go from nose to tail of the resultant vectors. So that's a plus b in red here. Okay. So let's look at this in component form. So we've said that a going from 0 to 2 along and 4 up. So you've got 2, 4. B is going to be 6 along and going down negative 3. So you go 6 along, negative 3 down. So that's B. Now A plus B should be 2 plus 6 on the x-axis. So that would be 8. And 4 minus 3 and 1 going up. And you can calculate it if you want. 1, 2, 3, 4, 5, 6, 7, 8 along and 1 up. So A plus B is just 8, 1. So that means we can add the components themselves if we wanted to represent the vectors. Okay.
Would
So
you all see a question like that? Would you always get that on like the squared paper so that you can work it out? Or would they tell you?
So they might give you like, oh, there's a vector A which is 2, 4 and a vector B 6, negative 3. Now can you
Right.
calculate A plus B? So
Right.
you could, if you want, if you didn't know the rule that you can just add the x A and x B together, like x1 plus x2 and then y1 plus y2. If you get a blank, you don't remember, and you could visually see it better, then it's up to you. You're allowed to draw,
They
but I'm not sure if the paper that you will get will have squares on them.
The ones I see in the exam papers are like that. Yeah, they're kind of written with two components, and then
Yeah.
you've got a calculation in relation to.
You've got to add them basically, but it's quite easy. It's just adding or taking away or multiplying by by what we call a scalar in front. So arrow must be nose to tail. So you go from the nose to the tail. So now, can we add these vectors? So addition of vectors, let's have a look here. So if AB, so to go from A to B, we go 3 in X and 4 up. And BC, we said it's going to be 2, -5. Now, AB plus BC, so AB, so from going from A to B, then B to C, should give me AC, right? Let's see, 3 plus 2 is going to be 5. So 1, 2, 3, 4, 5 along. And then 4 minus 5 is -1. So that's correct. So you can add AB plus BC, and that will give you AC in component form. So that's how you add vectors. Okay, so the trick that I use is whenever you're going to have two letters following each other, they cancel each other vector-wise. So you see the B and the B, because they are the same, the nose of one start the tail of the other one, then you cancel them and you end up with AC. Okay. So if I had AB plus BC plus CD plus DF, it's the same as AF. Every two letters will cancel each other. Okay, so let's have a look. So 3, 4 plus 2, 5, we said 5, -1. Now, so AC is 5, -1. In general, we have for vector U and V, if U is given in that component form AB and V CD, so AB just means a value for A, a value for B, any value, and any value for C, and any value for D. Then if you add the two vectors, that means you need to add the 2x component of each and the 2y component. You end up with A plus C for the x and B plus D for the y. Okay, easy enough. You just add the x's and you add the y's. Now, what do we call a zero vector? And that exists, by the way. It does exist. So if I was to go from A to B, okay, and I decide I'm gonna go back after B back to A, so AB plus BA is going to give me AA because I've not moved. So if you've not moved, you don't have any magnitude and you don't have any direction. We call that you've just back to the same point. You've not moved, so it's what we call the zero vector. So if AB is 1, 2, then BA is -1, -2. If you add 1 minus 1, it gives you 0, and 2 minus 2, 0. We call this the zero vector. So don't be surprised if you do some sums and you end up with 0, 0 and thinking, oh, that doesn't exist. It does, okay? So we call that the zero vector. And sometimes you see it written with a 0 and an underline under it. And if you see that in any paper, they mean the vector, the zero vector with component here, 0, 0. Okay. So in terms of physics, if someone says something about, oh, I've got a particle, it's moved that direction back to here, and the displacement is going to be 0 because you went back to where you started. Okay. So we've added vectors. How do we subtract vectors this time? So think adding a negative vector, basically. So if I've got U, oops, is that still there?
Mm-hmm.
I need to put it back into presentation. See, if I've got U and I've got V, and I'm told to subtract the two vectors, it's just adding the negative of V. So changing the direction of V and keeping it into that same direction. So it's just changing direction for V. So it's U minus V is the same as U plus negative V. And remember, I've mentioned that quite a few times. Sometimes when you taking away, it's adding the negative. So if U is 6, 3, whereas v is 1, 3, you just need to add -1 and -3. So minus v is going to be -1 minus 3. And if you put nose to tail, you will end up with 6 minus 1 which is 5, and 3 minus 3, which is 0. So you've not moved on the y-axis, but you've stayed on the x-axis by a magnitude of 5 here. Yeah? So u plus minus v is u minus v is just 5, 0. Okay, so that's how you subtract vectors. You just add the negative. So let's have a look. Subtraction of vectors. So if we've got a minus b, so if I was to follow this path, so I'm going in the direction of a, then I'm going opposite the direction of b. So that's an a minus b, and the resultant vectors is just called a minus b. Okay, because if it was a plus b, then you would go from this point to that point, and you would end up right to the top there. So if a is 6, 5 and b 2, 4, a minus b is just 6 minus 2 and 5 minus 4, which is 4, 1, and you can see it there. So we've added vectors, we subtracted vector by adding the inverse. So in general, again, to subtract vectors, if u is ab and v is cd, to just do u minus v, you just do a minus c and b minus d.
Well, they always give you an instruction as to whether you've got to
Subtract. Yeah, they will
give
tell
that
you. Yeah, they will tell
Like-
you calculate. Yeah, evaluate or calculate u minus v or 2u plus v. So you need to do 2 times a, 2 times b. So we're going to see that.
Cool.
Okay, and for the first homework, you'll see it's basically the question you've been asking. So it's chapter 28. We've got 28A and 28B. These are the star questions. It's the type of question you could get during an exam, basically Q1 and 2, question 1 and 2, and question 4 and 9. And it's just practicing these u plus v and 2u plus v. So in this one, exercise 28A, you'll see, write each vector in component form. So you've got AB. Remember, you go 2 along, 6 up. So in component form, AB will be 2, 6. CD, so it's going to be 1 along and 6 down. So 1, negative 6. EF, so we go on the left this time, so it's going to be negative 2 along and 5 up. So negative 2 plus 5. So you know the drill basically. Okay, and if it's a horizontal line or a vertical line, one of them is 0. So if it's horizontal, you've got x, a value. If it's vertical, you've only got a y component form. But you need to write 0 for the other one. Okay. So the first one exercise is to just write in component form. So we can just put one of them as an example. So we're going to do, we can do FE if you want. So basically here you're expected to be able to say FE, which is a vector FE, so you can put an arrow at the top, equal. So component form, we said we go in 2 on the left, so that's negative 2 in terms of x coordinate. And we go in 3, 4, 5, 5 up. And that's it. That's FE for you. In this case here, we've been asked to sketch. So they've given us the coordinate. We've got to sketch it. So same thing. I'm going to pick this one, for example. So if I was to sketch this, I'm going to put the first point I. So I've been told to go -2 on the x-axis. So imagine we've got proper coordinates. So that'd be -2 and then 5 up. 1, 2, 3, 4, 5. So you put your j there. Get a ruler. Join those two properly. Straight line. And let's put a vector there. And that's us. We've done ij, ij. So you can rub that out. Okay. Simple enough. Just think about coordinate x and y. So I think that's the same thing, isn't it? AB25, yeah. So I've given you in the paper some squares, so you'll be able to do it. So here you've got AB equal 25. So that would be 2, 5. So I don't even know why I've got 2 there. Yeah, so AB should have been here. Not sure what this is coming from. Yeah, so it's just an example. It's not the AB that is here. So IJ, so you can draw it on this paper here. So these are the type of question you would see in Nat 5, for example. Calculate the resultant vectors, and we've got here A, B, C, or D. So we can do one of them. We can do, let's do B. It's got a negative in it. So if I'm asked to calculate B, you just go, okay, this is -2, 5, minus, so W, so it's 0 and 2. So -2 minus 0 is the first coordinate here. 5 minus 2. And then you finish writing that in component form. That's -2. Taking away 0 is just the number itself. 5 minus 2 is 3. So that's the first one. So x minus w. So you'll see them written in bold, right? But because we can't write in bold ourselves, you just put the underline there.
Is x not supposed to be 6, 4, Adrian? Is that not?
Oh, sorry.
I just spotted that,
I put
sorry.
V. No, you're right. You're right. I put V.
It's Easter holidays, don't worry.
Well spotted. I know, it's getting a bit late. So, eraser. Yeah, so it should have been, sorry, it should have been here. 6, 4.
So those questions are quite, I just, when I saw some in past papers, I was kind of like, I was thrown, but I now can understand it, because obviously they asked me like 2u plus w, and obviously the values, it's quite simple, but they're not worth like loads of marks.
Yeah, no, they do give a lot of marks.
1 or 2, I don't think they're like.
And they're not difficult at all, because it's just simple math, because the numbers as well are never too complicated. They might throw, if they want to make it a bit more challenging, like a fraction, like a half, for example, for one, and then 3/5 on the other one, but you just do the same thing. It just means they are testing you for not just the vector understanding, but if you can manipulate fractions, for example. That could be, but I've rarely seen it. It's usually quite simple like this. So 6 and 2 is x minus w. This time I got it okay, yeah, 0, 2.
Yeah.
I don't know why I went for V.
I was actually.
Oh, because it started with V at the top.
Yeah, you just.
Yeah, I just went okay, so it's got to be that one. Plus we always write x first, and anyway, so you got the hack. This is very simple. So if you got 3 of them, you just do the first 2, and then you do the next one, a bit like you would do with BODMAS.
Yeah.
So these are the type of question that you could see that could be used in terms of if I was to design a game, for example, I could set my game so that I can change the river flow. So you'll have a wee function that changes the speed of the river, but the river flow can change in X or Y direction. So in this case here, you've got the river flow going -5. It's kind of a force tending to push you that way with a -5 type unit force. Whereas you've got a wee swimmer here, he's trying to swim across the current. Okay, so he's working hard on the y-axis, so you can see, but he's got to fight against the current. So he needs to work on the x-axis at the same time. So if he wants to end up here, it will end up here if there was no current at all. But because he's swimming using that quantity of force, you can see that physically he's going to start drifting like down here because of the river flow. So now just using that, you could say exactly where he's going to end up when he reaches, the other side. So what you would do is you would say, okay, I need to find the resultant vector. So it's 3 minus 8. So you just add them. So you've got 3 minus 8 plus -5 and 0. So that's going to be -2 and -8. So technically, instead of moving 3 here, so imagine if this was 1 unit, 2 unit, 3 units, he's going to end up here in the -2 region. He's going to end, if he swims and there's a current like this, he's just going to drift like that. And that is used in boats as well. So when they navigate, they can tell exactly, depending on the force of the current, by how much they need to sail, for example. So you position your sail in a certain direction, and then you know that you're going to end up here. Okay. Now, what would be the effect if the river flow doubled? So you just double that. So then you would say, okay, it's going to be 3 -8, and you double this. So 2 times -5 and 0. So that would be 3 -8 and -10 and 0. And you could see it's going to be -7 and -8. So it's a bit like, instead of being a -2, it's going to go down to -7. So it's going to be much further along. Okay. So what do we call position vectors? So sometimes you will hear people mentioning something about position vectors. And what they mean by position vector is they've now added what we call the 0 point here. So the origin of my coordinate here is this point 0. So if I'm looking to draw the vector AB, I can use OA and I can use OB. So to go from A to B, what I would need to do is go against OA, which means minus OA, and then plus OB. And then that means I can reach AB. So now let's see what it's going to do to our component form here. So I've got 2 points, and I've been asked to find the component. So if OA is 3, 4, remember, so it's 3 along 4 top, so which is 3, 4 in coordinate, and OB 5, 2, so 5 along 2 up. AB should be 2 along, -2 down. So how do we get 2 along and -2 down? You need to do 5 minus 3, yeah, and 2 minus 4. So to get AB, you need to do OB minus OA. And that would give you AB. Okay. So if you're given 2 points, you could be asked to find the coordinate of the vector of those 2 points. So you can draw it if you want, it might be easier, or you can just say it's the coordinate of B in component form minus the coordinates of A. So AB is B minus A, with B being 5, 2, and A being 3, 4. Okay, so even if you couldn't remember, you could always draw a wee sketch for you to help you. Okay, so that's what they call position vector. So OA is called the position vector of the point A because it's a position relative to the origin O. And we write it as A, so small a. And OB is the position vector for the point B. Again, we write it underline B. AB is just B minus A. So AO plus OB, remember the O and O cancel each other, AB, but AO is the opposite of OA, which is minus A, or B minus A. Okay. So that's an important one to remember. So whenever you're going to be given 2 points, AB, so you take a note of that. AB as a vector is just the point B minus the point A in its components. Oops. Okay. So that is the question we could be asked. For example, if P and Q have coordinates 4, 8, and 2, 3, respectively, so P is 4, 8, Q is 2, 3, find the components of PQ. So instead of AB this time, we've got PQ, so it's going to be Q minus P. So X of Q is 2 minus 4, so that's going to be minus 2. And 3 minus 8, which is minus 5. So if someone asks you, find the coordinates of, find the components of PQ. So coordinates, remember you write them horizontally, whereas the components of a vector, we always write them vertically. That's the only difference between vectors and point. So if I've got on a graph, P is 4 and 8 for the points, Q is 2 and 3. Now PQ, like we said, is going to be 2 on the left, so negative 2, and 5 down, so minus 5. So PQ, if you do Q minus P, you get PQ. Negative 2, negative 5. Okay. So remember we said we've got a direction, which is represented by the arrow where it's going, and a magnitude. So how do we find the magnitude of a vector? So let's think about it. So the way we represent it, we put what we call absolute bars around it. So we put these bars. So these are usually called absolute value. They're always positive. So a magnitude is always positive, and they represent here the length of that vector. So if you use Pythagoras, because you've got a right angle triangle, okay, so let's say you've got to find the magnitude of this vector here, U, PQ, because we said we go 4 along, 3 up. So for this vector here, PQ, which is 4, 3 in components, the magnitude is just going to be square root of 4 square plus 3 square, which gives you under Pythagoras the length of that hypotenuse. So PQ is just square root of a square plus b square. So if you've got two components and you're asked to find the magnitude of the vectors, you just take the square roots of each component square. So let's say you've got CD. You've got CD, which is 4 and 2. So if I'm asked to find the magnitude of this vector here, you would just do square root of 4 square plus 2 square. So that would mean square root of 16 plus 4, which is square root of 20. Can we write it in the simplest form than 20?
2
Sorry?
root 5.
Yeah, 2 root 5. So at National 5 level, they expect you to be able to write anything that you write, fractions or sorts, etc., always in the simplest form, okay? Even if they don't ask you, put it into in simplest form, just write it down in its simplest form. Okay. It's the same on the prelim 1. Remember, we had that root 8. We needed to change that into 2 root 2. So just to show that it doesn't matter what direction it goes, the magnitude, because we're going to do negative 4 square, it's going to be 16. 3 square is going to be 9. So 16 and 9 will be 25. So this here is going to be root 25, which is about 5. So if you've got a right angle triangle, one side is 3, the other side is 4, the length of the longest of the side is always going to be 5. Yeah? So this is what we call a perfect right angle. So 16 plus 9, which is 25, root 25 is 5. Okay?
Yeah.
So even if they don't say calculate the magnitude and they put these vertical lines across it, they might say calculate, absolute value of W, the vector itself. They just means calculate the magnitude. And you just use Pythagoras. Okay. So now, why do they use vectors? Is in general to find what we call a finishing point. Remember, as far as vectors concerned, only the finishing point in relation to the starting point is the important part. Okay. No matter what route you take, it's not the most important part. It's where you end up. It's the displacement that you've achieved. Okay, so let's see here what kind of journey we can take. So if I was to go from W to Z, it doesn't matter. Given that ZY is twice here, so we've got ZY, which is twice WX. So what they've told us here is ZY is 2U. Find WY. So they've asked me to find this vector here from W to Y. So to go from W to Y, I'm going to use what they've given me so far. So they've given me U, which is WX, and then they've given me V, which is XY. Remember, so WX plus XY is going to give me WY. So if you're asked to express WY, you just say it's U plus V. To go from W to Y, I need to go along U first and then go along V. Okay, so that should be the easiest one. So we're going to look for WY, WZ. So going from there to there. To get WZ, we can go along WX, along XY, and then do YZ. Remember what I said? WX plus XY plus YZ is going to be giving me WZ. So you might say, oh, how do you know YZ? I know what ZY is. ZY is 2U. They've just told me twice WX. So YZ is going to be minus 2U, the opposite direction. Okay, so let's have a look. If zy is 2u, wy is u plus v. Okay, so we're going to go from u to v. And then wz is going to be u plus v. Now, we are against 2u, so that's why we need to flip it to make it negative, minus 2u to get to z. Yeah? Are you seeing the wee trick that they use? So whenever you're going to go against an arrow, it just means you're taking the opposite of the vector associated to it. So if you go with the arrow in that same direction, it's going to be plus, so u, so plus u plus v minus 2u.
Doing the opposite.
You go the opposite, yeah.
Doing the opposite what it says.
And now you group the likes. So I've got a u minus 2u, that's minus u, plus v. Now xm, so if I'm asked to find xm, we can go, it's just m is halfway between x and y. I think it was said in the problem. So let's see, xm, given that, no, they've not told us. They should be telling us that m is halfway between x and y. So xm is half xy, which is just half v. So if xy is v, okay. Zm this time, to get from z to m, we can go zy and go opposite my, ym, sorry. So zm is going to be minus 2u minus half of v, because v is xy. So half of v against it become minus half of v. Yeah? Zm. To go from z to m, we need to do zy minus ym. Okay, so magnitude-wise, it's just xm and ym are the same. So for homework 2, we've got 15.6, question 1 and 4. Let's have a look. They're probably going to be very similar to what we've just done. Oh, this is National 5. So you probably don't have that book, but what I've done is in here, I've put you the pictures that you need from the National 5 book. Okay, so sometimes you get questions like this, and Lecky doesn't have many of these, so I pulled them from the TJ book, but you've got the question here. So I've said to do question 1 and 4. So let's have a look. Question 1. So these are the type of question you might get, and unfortunately, Lecky doesn't do many of these, and that is called the going from one point to another. So here, what are they telling us? We've got a parallelogram, PQRS. PQ equal U, yeah, so that's, and PS equal V. Now, find the following vectors in terms of U and V. So if they ask us to find QR, remember what we said, equivalent vectors. So this vector here is equal to this vector here.
Yeah.
We've got the same direction and the same magnitude, because that's why it's a parallelogram, right? So if someone asks me what is QR, you just say it's V. Even when they say in terms of U and V, I've only got V here. That means it's 1V plus 0U basically, which is just V. For SR, okay, I've got the same thing here, PQ. So that's SR. That's U. So you just say SR equal U. It's the equivalent vector. Now things are going to get a bit more complicated because they've asked us to go PR. But look at PR. I can use a path that has got V and U on it. You can go from P to S and S to R. And all of them, I'm going to the same direction as this vector. That is just V plus U or U plus V. It's the same thing. So I've written PR in terms of PS plus SR. So PS is V, SR is U, so V plus U. Yeah? QS, I'm going to use this path this time. So I'm going to go from Q to R, which is V.
And then U.
And then I'm going to go against U, remember?
Oh yeah.
It's the opposite direction. So then you take away, yeah, subtract U. So if you go in the same direction, it's a plus. When you go opposite, you just flip it around by subtracting it. And you've seen here QS, we could have gone that way as well. So minus U plus V that way, which is the same thing. You would go against U and V. So there's more than one path. PM, so PM is halfway here. So how can I get from there to there?
You could do half
So,
U.
yeah, so I can go, so for PM, I can say, okay, if I go, I'm trying to think, what would be the best way?
Like, can you not just go straight from P to M and just do that half as U?
It would be half U if it was half here. So I need to find a path
Yeah.
to get me there. So it's half of PR. Because there's PR, right? And
Yep.
PM basically is just
Equivalent.
half of PR itself. And did we do PR already? Yeah. So it's half of V plus U. And that's us. We've written it in terms of V, U and V. Okay. So it's half of V plus U. And remember, when you put the brackets, you need to open and close them. SM is half of SQ. But we've done QS.
Yeah.
So we need to change the sign of QS. So if QS is V minus U, SQ is just minus V plus U. You just change the sign, and that's true. SQ is negative V plus U. Or you can write that as U minus V. So now to write half of SQ is just half of U minus V. Okay. So you just need to play around with it and see which path to take. But if they ask you to find PR, for example, it's for a good reason. You're going to probably need PR to find some other things.
Yeah.
Let's see. This is the second problem. Yeah. So that's the last problem for today. I've got trapezium U V W X. We've been given UV is H, the vector, in terms of magnitude, distance, or whatever. VW is K. XW is 2UV. So I can what the good thing is just write down what you've been given on the diagram itself. So 2UV is 2H. So basically, this length here, you double it, and then you get the length at the top. Find these vectors in terms of h and k. So xw, we've just done. uw is just going to be that plus that. So to get from u to w, I need to go through h and add k to it. Yeah.
It's easy.
To go from v to x, I can go v to w, that's k,
And then W to X.
Yeah.
and then w to x, which is going to do against 2h, which is going to be minus 2h. Yeah.
Mhm.
And from u to x, then I'll just go all around h plus k minus 2h, and you've got your ux. Okay. So xw we said was, what was xw again? 2h?
Mhm. Two times.
2h, yeah. So you can finish ux. So now what they've told us is, in fact, h is 40. So if you were to use that, okay, 40, and k in component form is 2, 4. So you can see 1, 2 along, and 4 up. 4 along with 0 up. Okay. Now find the component of xw. So xw is 2h, right?
Two
So
zero.
you just say, yeah, xw. Oh no, I just pressed the wrong button. xw is 2h. I didn't know this.
I'll be in
It's,
the corner.
yeah, no, it's my pen. My pen basically it's got like a wee mouse type button on it, and by mistake I press on it. 2h is going to be 2 times 4 and 0, which is just 80, yeah. So that'd be xw. Remember to put the proper vector line. Now, if they ask me to find uw, so uw was h plus k, wasn't it? Yeah, h plus k. So you just add those two vectors. H plus k is going to be 4 plus 2, that's 6, yeah?
Yep, 6, 4.
And then 0 plus 4, 4. Now we're going to do C. Find the magnitude of uw. Pythagoras. Square root of 6 square plus 4 square. 36 plus 16, which is 52. Can we simplify that? So let's think about it, right? 52, is it odd or even?
Even.
Can I half it?
Yeah.
Yeah. What do I get?
20.
26.
Yes.
26, is that even?
Yeah.
Yes.
Can I half it?
Yeah.
13.
If you can half a number twice, that means you can divide it by 4. That means we can rewrite 52 as 4 times something, which is 4 times 13. So that's how you would manipulate the numbers. Even, half it. Still half, still even, I can half it again. That means you can extract 2 root 13 from it. And that would be a question with no calculator, asking you calculate the magnitude of UW and give your answer in its simplest form. So you would do all this, get a mark for this, and get a mark for the salt. Okay? So whenever you're going to see somewhere written simplest form, think about you need to manipulate that number. And that'll be us for today. So the other one, you'll try and find it back, or if you can't find it back, like Kirsty just mentioned, you can fast forward the record right to the end, and you should get most of these. Okay, so then it's not complicated. You just need to take your time and just walk your way and practice a few. And I'm sure vectors, yeah, most of the time people would get them.
I've seen them in past papers, as I've said earlier. I can now recognise just what to do.
Yeah.
They aren't too like out there.